So chapter 13 is all about solutions. At the beginning of the semester, we briefly touched upon solutions. What a solution is a homogeneous mixture. If you recall, a homogeneous mixture is a mixture that is uniform. So we're going to talk about what exactly is a solution, the different kinds of solutions we can see, solubility, and introduce a new unit, the unit of concentration. So a solution is a homogeneous mixture. Solutions consist of two parts. You have a solute, which is the thing that is being dissolved, solute, and you have a solvent. The solvent is the thing that is doing the dissolving. So in terms of amounts, solute is the thing that you have less of, solvent is the thing that you have more of. And by less and more, I'm talking about number of moles. Recall from chapter 8 what a mole is. 1 mole is an Avogadro's number of whatever we're talking about. So a mole of water, for example, would be Avogadro's number of water molecules, which would be 6.02 times 10 to the 23rd. So something like salt water, that is a solution. It is a homogeneous mixture. It is sodium chloride, which is the solute, dissolved in water, which is the solvent. Solutions can exist in all three phases. You can have a gas dissolved in a gas, you can have a liquid dissolved in a gas, you can have a gas in a liquid in a liquid, a solid in a liquid, or liquids and solids and solids in solids. So the most common types of solutions that we're going to talk about are the liquid solutions, gas in a liquid in a liquid, and a solid in a liquid, with the focus being on the solid dissolved in a liquid. These are the bulk majority of the solutions that we work with or have worked with in the lab, and the majority of solutions that you will see in your future chemistry classes. So a couple examples of these various types of solutions. A gas dissolved in a gas. Here the example is air, the air we breathe. So the air we breathe is composed of nitrogen gas and oxygen gas. It's about 80% nitrogen, 20% oxygen. So what would the solvent and solute be here? For air, the solvent would be nitrogen gas, because that's what there's more of, and the solute would be oxygen gas, because that's what there's less of. So focusing on the liquid types of solutions, the first one we're going to talk about is gases dissolved in solution and what impacts their solubility. So let's talk a little bit about this word, solubility. What does solubility mean to you? Think back to chapter 7, the solubility rules that you learned with the double replacement reactions. If things were soluble, what did that mean? What phase were those chemicals that were soluble? If things were insoluble, what did that mean? What phases were those? So solubility in essence refers to how well things get dissolved. If something has more solubility, it dissolves more, it dissolves easier, it dissolves better in solution. If something has less solubility, then it dissolves less in solution. So the things that we're going to talk about are only for gases dissolved in liquids, all right? So we're going to talk about temperature in a few different examples, but the thing with how temperature affects solubility is temperature affects solubility differently if you're talking about a gas in a solution versus if you're talking about a solid in a solution. So it's important to keep that in mind. As long as we're talking about gases in solution, temperature and solubility are inverses. So what that means is that if you have a gas, and again, this is only for gases dissolved in liquids, if your temperature goes up, the solubility of your gas goes down. So let's talk about a typical example of what you can expect to see as a gas dissolved in a liquid. And so an example that we're all familiar with would be something like a carbonated beverage, like seltzer water or soda or beer or what have you, anything of that nature. So in that case, the solvent is water, and the solute would be the carbon dioxide gas. So what happens when you heat up your soda, or what happens when you heat up your beer? One, it's going to taste gross, but also what happens to the CO2 numbers? What happens to the solubility of CO2? So as the temperature goes up, the solubility of your gas goes down. So think about how you store soda. When you buy soda from the store, you put it in the refrigerator. You don't put it in the oven, right? So the colder you keep this solution, the colder you keep your soda, the colder you keep your beer or whatever your gas dissolved in a liquid solution is, the more gas stays dissolved. So the colder it is, the more the gas stays dissolved. That's why if you just have a soda that's just open at room temperature, it'll go flat faster than a soda that is cold and open. So now we're going to talk about pressure and gas solubility. And again, this is for solutions that are a gas dissolved in a liquid. So the higher the pressure, the higher the solubility of your gas dissolved in your liquid. And you can see the relationship here is direct. As I double the pressure from 1 to 2 atmospheres, I double the solubility. As I triple the pressure from 1 to 3 atmospheres, I triple the solubility. So that is a direct relationship. Again, let's think about the example of the soda or the beer. You have your soda in a closed bottle. The pressure is very high inside that bottle, so the gas stays dissolved. As soon as you open that soda or that beer, what happens? You hear that hissing sound, and you can physically see bubbles. You can physically see all of the gas escaping. And the reason for that is by opening that beverage, that soda or that beer or whatever, you are decreasing the pressure, and so therefore you are decreasing the solubility of your gas, and so all the gas starts to escape. So liquids in solution. We talked a bit about dipoles and what polar means in the chapter 12 slides. And so if you recall, things are polar when they have polar covalent bonds and when they have asymmetry. We can see here that this water molecule, we remember from chapter 12, this is the bent shape. It is asymmetrical. It has polar bonds, therefore this is a polar molecule. So the rule for liquids dissolved in liquids is like dissolves like. So what that means is that polar liquids dissolve in other polar liquids, and nonpolar liquids dissolve in other nonpolar liquids. And again, the solute is the thing that there is less moles of, and the solvent is the thing that there are more moles of. So here in this slide, we can see an example of some polar liquids and some non-polar liquids. So again, the rule is like dissolves like. So I can dissolve methanol in water, for example, because they are both polar, but I cannot dissolve hexane in water because hexane is non-polar. They won't mix. And you did this in one of your first labs. You could see physically the two layers form, where one liquid has a layer that floats on top of another one. Think salad dressing, oil and vinegar. Oil is a non-polar liquid, and vinegar is this stuff here, acetic acid. This is a polar material, and so they don't mix, they don't dissolve into each other. And so when two liquids mix, the word here is miscible, miscible. When two liquids do not mix, we say they are immiscible, immiscible. So just reiterating here, like dissolves like. Polar liquids dissolve in polar things, non-polar liquids dissolve in non-polar things, but they don't dissolve in each other. So here are those two words again, miscible and immiscible. So here's our example of salad dressing. We have the oil on top, non-polar, the water on bottom, that is polar. This is an example of immiscible liquids and therefore a heterogeneous mixture. Two liquids that completely dissolve in each other, like methanol and water, they are miscible and they form solutions, which are homogeneous mixtures. Remember, all solutions are homogeneous mixtures. So the rest of this chapter focuses on this type of solution, solids dissolved in liquids. And you can also predict whether or not a solid will dissolve in a liquid by applying the like dissolves like rule. Polar solids dissolve in polar liquids, non-polar solids dissolve in non-polar liquids, and by using your solubility rules that you learned in Chapter 7. And so we'll see bullet point 1 in a video in a few slides. So what happens when a solid dissolves is the solvent particles kind of rip apart the solute particles and surround them in what we call solvation cages. And they stay dissolved because the solute particles are more strongly attracted to the solvent particles than they are to each other. So typically ionic compounds, remember from chapter 6, how do we identify when something is an ionic compound, are soluble in polar solvents like water and insoluble in non-polar solvents. So ionic compounds dissolve in polar solvents, but not in non-polar solvents. Polar compounds, example here would be something like sugar, are soluble in polar solvents and insoluble in non-polar solvents. And non-polar solids, example here would be this guy, naphthalene, they are soluble in non-polar solvents, but insoluble in polar solvents. So the dissolving process, you have your solid, your solute that you put inside your liquid, your solvent. So what happens is individual solvent molecules surround an individual solute molecule and create what we call a solvation cage. And so this here is preventing the solute molecules from sticking back together again. And so similar thing happens with ionic compounds. And you can see how, so we have our sodium chloride, we have our chloride ion in green, our sodium ion here in purple, and you can see how the orientation of the water molecules are different. So in the chloride example, the water molecules are oriented so that the positive pole of the water molecule, the H's, are pointing towards the chloride ion. And in the sodium example, the negative part of the water molecules, the oxygens, are pointing towards the sodium ion. And again, they form that solvation cage. So here is a video showing how water dissolves an ionic compound. So you can just watch this. So now that you've watched the video, you understand how solvents dissolve solutes. What we're going to talk about are some factors that affect the solubility for our solid and liquid solutions. And again, these are only true for solid and liquid solutions. So the first thing you can do is you can heat the solution. By increasing the temperature, what happens is we increase the solubility of our solid in our liquid. Contrast this to the beginning of this presentation when we talked about gases dissolved in liquid. How did the temperature impact the solubility of the gas in the liquid? It was the opposite. So for a gas in a liquid, heating the solution decreases the solubility. But for a solid in a liquid, heating the solution increases the solubility. The second thing you can do is you can stir the solution. Physically stirring the solution means you are increasing the amount of contact between the solvent molecules and the solute molecules. More contact means more dissolving. And the third thing you can do is increase the surface area of your solute. Think about trying to dissolve a solid sugar cube versus trying to dissolve that same mass of sugar but as a loose powder. What you will find is that the more finely ground up your solute is, the easier it is to dissolve. And the reason for that is you'll have more surface area for the solvent to attack. So doing these three things will increase your solubility of your solid in your liquid solution. So this graph shows the relationship for some compounds between solubility here on the y-axis and temperature here on the x-axis. And you can see for all of the compounds, it is a line that increases. Sometimes it increases very sharply, like here, the glucose, the sugar one. Sometimes it increases very shallowly, but across the board, it all increases. And so in general, as you increase the temperature, the solubility of your material increases. So solubility has a number. It can have a number associated with it. And we define the solubility as the maximum amount of solute that can dissolve in 100 grams of water at a given temperature. So erase some of these. All right. So solubility isn't an infinite thing. I can't just keep adding solute to my water and it'll keep dissolving. Eventually you'll hit a point where the more you add, it doesn't dissolve anymore. It just clumps up on the bottom of your container. And so that point we reach, solubility, we call that a saturated solution. So a solution containing exactly the maximum amount of solute at a given temperature, we call that a saturated solution. And we find that by looking at the graph on the previous slide. So if you look up for one of the compounds, you look at a temperature, you bring that over to the y-axis, it'll say how much you can dissolve at that temperature, that amount, we call that saturated. Saturated means I have dissolved the max, and if I try to dissolve any more, it won't dissolve. A solution that contains less than the maximum amount of solute is unsaturated. And a solution that has more than the maximum amount is called supersaturated. And we can make supersaturated solutions under certain conditions. So here is an example of another solubility graph. So we have temperature on the x-axis, we have solubility on the y-axis, and we can follow this purple line, and that'll tell us, for example, at, let's say, right here, at 50 degrees Celsius, what would saturated be? So we go up, okay, 50 degrees, we go across, that looks like about 90 grams. So at 50 degrees Celsius, I can dissolve 90 grams of my solute, which is sodium acetate, in 100 grams of water. At 50 degrees, what if I dissolve 50 grams? So at 50 degrees, I dissolve 50 grams. That puts me right here. What kind of solution do I have? Because it is below the saturation line, we have an unsaturated solution. What if I tried to dissolve 100 grams at 25 degrees Celsius? So 100 grams is right here. 25 degrees Celsius is right here. So we draw the line. That's above the saturation line. So that won't work. So what do? To create a supersaturated solution, what you have to do is you have to heat it up. So let's say I heat up my solution to 75 degrees Celsius. At 75 degrees Celsius, look at that. At 75 degrees Celsius, dissolving 100 grams of solute is unsaturated. So we heat up our solution to 75 degrees Celsius. We dissolve our 100 grams of solute. It is unsaturated. We then cool our solution back down to 25 degrees Celsius. And if we let it cool down gently and don't disturb it, what will happen is we will still have that same 100 grams dissolved, but now we are above the saturation line. We have created what is called a supersaturated solution. So in short, to create a supersaturated solution, what you do is you heat up your solution, you dissolve your solute, and then you let it cool back down to the temperature that you want, and you will have created a supersaturated solution. So we are introducing a new unit in this chapter, and that unit is the unit of concentration. So concentration tells us how much solute is dissolved for a given quantity of solution. And the units associated with concentration are mass percent and molarity. So the first one we're going to talk about mass percent, and then we'll talk about molarity in a little bit. So mass percent, we discussed this unit at the beginning of the semester. Mass percent is the mass of what we're talking about divided by the total mass converted to a percent. So if we're talking about a solution, the mass percent of a solution is the mass of your solute divided by the total mass of solution times 100%. And the mass of the solution is calculated by adding the mass of your solute plus the mass of your solvent. So another way to express mass percent would be mass of solute divided by mass of solute plus mass of solvent times 100%. So here's an example problem. We have 5 grams of sodium chloride and we dissolve it in 95 grams of water. What is the mass percent? So probably the most common mistake that I would see here would be people doing something like 5 grams divided by 97 times 100%. So why is this wrong? Because 97 grams is not the mass of the solution, it's only the mass of the solute. What is the total mass of solution? It's the 5 grams plus the 97 grams. So how do we calculate the mass percent here? Is we take the 5 grams of sodium chloride, divide it by the 5 grams of sodium chloride plus the 97 grams of water to give us 102 grams of solution. Calculate that out to 4.9%. So anytime we have a unit that is a fraction, like we do here with mass percent, we have a conversion factor. So what does this 4.9 mass percent means? It means that for every 100 grams of solution, I have 4.9 grams of sodium chloride. So we can write a conversion factor to express that relationship like this. So let's practice using mass percent as a conversion factor. So I have a 5.00 mass percent solution of dextrose, okay? And I want to know what mass of this solution will give me 25 grams of dextrose. So remember the questions when you're doing unit conversions. What unit do we have? We have grams of dextrose. What unit do we want? We want grams of solution. What is the relationship between those two? The relationship is this 5%. So we have 25 grams of dextrose. We write our units, grams of dextrose on the bottom, grams of solution on top. And this 5% means I have 5 grams of dextrose for every 100 grams of solution. So we have our setup. Now we multiply across, and we get our answer. How many sig figs should be in our final answer, by the way? We should have 3 sig figs. So 500 as written here only has 1 sig fig. I can make this have 3 sig figs by doing something like 5.00 times 10 to the second grams. So what this means is if I have 500 grams of solution, I have 25 grams of dextrose. So the next unit that we're going to talk about for concentration is molar concentration, and this unit is called molarity. So molarity is defined as the moles of the solute over the liters of solution. So pay attention to this aspect. It's liters of solution, not liters of solvent. So it's a subtle but important distinction. So you measure the volume after you've made your solution. You don't measure the volume of the solvent that you add. You add the solvent and then you measure the volume after, and that is your liters of solution. And so the symbol for molarity is a capital M, and again it is moles of solutes, moles, over liters of solution, and it's the most common unit that you will see during your chemistry classes. There is a slightly less common unit called molality, which is moles of solute over kilograms of solution, and that is one you will see less often, and we won't really discuss that in here. So let's practice calculating molarity. I have 24 grams of this compound. What's the name of this compound, by the way? NaOH is sodium hydroxide. So I have 24.0 grams of sodium hydroxide, and I make a solution with a final volume of 0.100 liters. What is the molarity? Well, remember molarity, capital M, is moles over liters. So what do we need? We need the moles and we need the liters. Well, do we have the liters? Yeah, sure we do. It's 0.100. But do we have the moles? No, we don't, but we do have the grams. And so what we do is we convert grams to moles using the molar mass and then divide by the volume. And so that's what's going on here. We are converting our 24.0 grams to moles by multiplying by the molar mass, 1 mole on top, 40.00 grams on the bottom. So this gets us the amount of moles we have, and then we divide that whole thing by the volume, 0.100 liters. We should have 3 sig figs. 3 sig figs in 24.0, 3 sig figs in 0.100 gives us 3 sig figs 6.00 molarity. Guess what, guys? We have another unit with a fraction, so that means we have another conversion factor. So molarity is moles per liter, so 6.00 molarity. We can express that as 6 moles over 1 liter over 6 moles, or even 6 moles over 1,000 milliliters, because these guys are equivalent. 1 liter is equal to 1,000 milliliters. So let's work through this example. How many grams of this chemical, K2Cr2O7, what's the name of this chemical, by the way? This is potassium dichromate. So how many grams of potassium dichromate are in this volume, 125.0 milliliters, of this concentration, 0.150 molarity? So what do we want? We want grams. What do we have? We have volume. What's the relationship between grams and volume? Well, we don't know. But we do know the relationship between moles and volume. That's the molarity. And we know the relationship between moles and grams. That's the molar mass. So what we're doing is we're using the moles over 1,000 milliliters form of the conversion factor, because we're starting in milliliters. So we have 125.0 milliliters. We want to convert that into moles. We want to convert that into moles so we can convert it into grams, because that's what the question is asking. So multiply by our conversion factor. 0.150 molarity, remember, is 0.150 moles over 1 liter, or 0.150 moles over 1,000 milliliters. So milliliters and milliliters cancel, and then we multiply by the molar mass to convert to grams. So moles on the bottom, grams on top. 294.2 multiply across, we get in 3 sig figs 5.52 grams. Okay, so let's try going the other way. I have a 12.0 molarity solution of HCl. What is HCl? HCl is hydrochloric acid. So what volume of a 12.0 molarity HCl solution contains 9.15 grams of the solute? So what do we want here? We want volume. What do we have? Grams. Do we know of a relationship between grams and volume? No, we don't. But we do know of a relationship between moles and volume. That's 12.0. So the first thing we need to do is we need to convert our grams into moles. We do that by using the molar mass. So 9.15 grams of HCl, grams on the bottom, moles on top, 1 mole over 36.46. So we are now in moles. So that means moles needs to go on the bottom. We can do 1,000 milliliters on top, or we can do 1 liter. Either way, you'll get to the same place. Multiply across, and we get our final answer in 3 sig figs, 20.9 milliliters of solution. So if a volume of a certain concentration solution is known, then you know how many moles you have. So volume V times molarity, capital M, equals the number of moles you have. So for example, here I have 200 milliliters of a 0.5 molarity solution. How many moles do I have? So we take the volume, convert it to liters, 0.200 liters, times the molarity, which is 0.5, gives us 0.100 moles. So we can use that idea, the idea that moles, number of moles equals volume times molarity when we are doing what's called dilutions. So what a dilution is when you take a more concentrated solution with a higher molarity, you add solvent to make it a less concentrated, lower molarity solution. So remember molarity, capital M equals moles divided by liters. So I can make my molarity go down if I keep my moles constant and just add extra liters. This is the essence of a dilution. So before and after you do a dilution, the number of moles of solute you have are the same. And because the number of moles of solute are the same, you can use this relationship. Initial molarity times initial volume equals final molarity times final volume. Let's see a couple examples of that. So here I have my initial solution, I, and then my final solution, F. So each one of these white blocks represents 1 mole. So in the initial solution, I have a volume of 150 milliliters, and I have 5 blocks, 5 moles. So what's the concentration of the initial solution? The concentration is 5 blocks, 5 moles over 150 milliliters, gives me a concentration of 0.33 moles per milliliter. In the final solution, I have added additional solvent. I've added, it looks like 100 milliliters of additional solvent, so I've taken the volume up to 250 mils. But notice how I still have those same 5 moles. What's the new concentration? So this time I have 5 moles and 250 mils instead of 150, which gives me a new concentration of 0.02 moles per milliliter. So between the initial and the final solution, the concentration changed, but the actual amount, that is the moles of solute, did not change. The only thing that changed was the concentration, and the concentration changed because I was adding volume. So I'm increasing the denominator of this fraction. So let's practice. So we have 300 mils of a 0.0500 molarity HCl solution. And I want to know what is the new concentration when I add 500 mils to that. So let's click the slide. Okay, we know what M1 and V1 are. Let's click the slide again. So what is V2 going to be? V2 is going to be my final volume, which is the 500 mils added to the 300 mils, which would be 800 mils. Click the slide again. So we have our problem set up. M1 is the 0.0500 molarity times 300 mils equals M2 times 800 mils. And so for this formula to work, you don't necessarily have to have your volume be in liters. The only thing that has to be true is that V1 and V2 need to be in the same units. So if they're both in milliliters, that's fine. If they're both in liters, that's fine. It's just you have to be consistent. So click the slide. Simplify the equation. Solve for M2. We end up with my final molarity being 0.01875. So here's another practice problem. What volume of 6.0 molarity sodium hydroxide needs to be diluted to prepare 5.00 liters of a 0.10 molarity solution? So let's assign our variables. We'll call 6.0 molarity sodium hydroxide, M1. What volume? That's what we're looking for. So that's V1. V1 is going to be our variable. 5.00 liters, that's V2 of a 0.10 molarity solution, that is M2. So take a moment, see if you can solve for V1. So click the slide to remove the box and reveal the answer. Okay, so chapter 9, we discussed stoichiometry and different types of stoichiometry problems. And we talked about moving across a chemical equation to convert from amount of one chemical to another chemical. Now, the concept of molarity introduces something new to that setup. Let's see an example on the next slide. So here we have a stoichiometry problem like we would have seen in chapter 9. But this time, instead of given grams, we're given volume and molarity. So the fundamental rule still applies, and the fundamental rule for stoichiometry problems is that in order to convert from one chemical to another chemical, you need to be in moles. So we are trying to convert from aluminum bromide, that's what we're starting with, to silver bromide. So aluminum bromide is this compound here, and silver bromide is this compound here. So in order to convert from aluminum bromide to silver bromide, we need to be in moles. That hasn't changed. What has changed is how we get there. So if I'm given 17.8 milliliters of a 0.105 molarity solution, how do I get to moles? Remember, we get to moles by multiplying volume times molarity. So we start with the 17.8 milliliters times milliliters on bottom, moles on top, 0.105 moles over 1,000 milliliters. So after this point, we are now in moles. And so we can use our molar ratio, that 3-to-1 relationship, to convert from moles of aluminum bromide to moles of silver bromide. And then finally, to get to grams of silver bromide, we multiply by the molar mass. Okay, so I'm going to break with tradition here a little bit, and I'm going to work all four of these problems with you guys. So here we have 31 grams of sodium chloride, molecular weight 58.44 grams per mole, are dissolved in 250.0 grams of water to make a solution with a final volume of 0.2500 liters. So it appears that all of our numbers are in 4 sig figs. Keep that in mind for later. First question, what is the solute? So recall that the solute is the fig that is being dissolved, and it is the fig that there is less of. And in this case, that is the sodium chloride. Solvent is the other thing, right? Solutions have two parts, a solute and a solvent. A solute is the thing being dissolved. A solvent is the thing doing the dissolving, which in this case is water. So third question, what is the mass percent concentration? So recall, mass percent concentration equals grams of solute over grams of solution. So we have 31.00 grams of solute divided by a total mass of solution, 31.00, plus the mass of the water, which is 250.0, which is 31.00 divided by 281.00. 31.00 divided by 281.00 in 4 sig figs gives us 11.03%. All right, so now let's erase this and make room for the last question. What is the concentration in molarity? So recall, molarity is moles of solute over liters of solution. Well, we already know the liters of solution, so all we need to do is figure out the moles of the solute. So let's do that. So we have 31.00 grams sodium chloride. We need to convert this to moles. 1 mole on top, 58.44 grams on the bottom. So we're going to be in 4 sig figs here. 31.00 times 1 divided by 58.44. And 4 sig figs gives us 0.5305 moles divided by the volume in liters of 0.2500 liters gives us 2.122 molarity. Okay guys, that is it for chapter 13. Any questions, please let me know by email.